Welcome. In this lecture and following sensor lectures, I will focus on active safety sensors and sensors for automated vehicles. However, as you will see, the intra-vehicle sensor types covered in this lecture are also used in passive safety. The title of this lecture includes the term intra-vehicle sensors. By this I mean sensors that measure aspects of the own vehicle, inside the own vehicle. In this lecture I will cover a few sensors in each of the two categories of intra-vehicle sensors: vehicle control sensors and vehicle kinematic sensors. Sensors for vehicle control include pressure sensors and angle or rotation sensors. Sensors for vehicle kinematics include, for example, vehicle X, Y, and Z acceleration and the angular rates of roll, pitch, and yaw. As you see, all of the sensors overlap with sensors used in the passive safety domain, although they are often used for different purposes. A typical use of pressure sensors in active safety systems and automated vehicles is to measure the pressure of the braking system of the car. This sensor captures changes in pressures, for example due to the driving pressing the brake, a braking system priming the brakes for faster response, or an active safety or automated vehicle system that controls the brake. When analyzing data from driving, it is important to know who or what caused the pressure changes. When driver behavior is evaluated, you should not by mistake analyze brake pressure created for, by example, adaptive cruise control, which is part of the vehicle system. Angular or rotary position sensors are used in several vehicle systems. Measuring rotation of the steering wheel is one such use. Another use is to measure the wheel rotations, for example to control stability control systems. The figure on the left shows the principle of a simple conversion of information on a rotary to an electronic signal. Every time there is a transition in the emitted light, for example black to white, the sensor registers motion. The figure on the right shows a binary encoder version of the rotary on the left, enable absolute angle measurements for the full revolution. The more separate radial fields A through C in the figure, the higher absolute angular resolution can be measured. Accelerometers are likely the most important sensor for passive safety, used for identifying and quantifying crashes and as a surrogate measure for injury measurements. But it's also a relatively important sensor also for active safety systems and automated vehicles. There it is, for example, used as a component in estimated positions over time, using angular rate sensors and accelerometers as a basis, so-called dead reckoning, as well as input to braking and steering control systems. The demands on accelerometers with respect to precision, accuracy, and low level of drift over time have increased significantly over the last few decades. What you see here is an accelerometer with a range of plus minus 4.9 Gs. This sensor is suited for example, dynamics control. Note the operating temperatures. Automotive sensors typically need to have a very wide operating temperature range. Working as, for example, an engineer, it is important to consider the following for accelerometers. The unit meter per second squared and G, gravity, are both used extensively. Make sure you know which units you are working with. Make sure you use an accelerometer with the appropriate range for your application. Don't use a sensor for crash severity measurements, for example plus minus 40 G, to measure vehicle kinematics that are typically less than 1 G. Angular velocity can be misinterpreted as linear acceleration through centripetal acceleration. Be careful. Integrated acceleration is speed, which integrates to distance. However, a small offset or error in the acceleration produces large errors in speed and distance over time. Be careful. Angular rate sensors typically measure in radians per second, but degrees per second are sometimes used. Again, be careful with the units. There are several types of angular rate sensors. The leftmost image is a prototype version of a micro-machined angular rate sensor. In the middle, it's one step in its evolution. The figure to the right is a production high-end one-axis angular rate sensor based on the same fundamental principles. The process from idea to final product can be up to 10 to 20 years. Examples of applications for angular rate sensors include closed-loop stability control, so-called electronic stability control, and as a component in inertial measurement units, IMUs. IMUs are, for example, used as components in vehicle positioning, and also called dead reckoning, where the positioning is based solely on own vehicle kinematics. Sensors used on the principle used in the images you see here have been included in millions of electronic control units for airbag deployments. Each type of sensor has its specific information it's related to, for example, its operation, filtering, and resulting data. This table is an extract of a sensor specification sheet for the angular rate sensor that was just described. Information here include quantification of how temperature and acceleration affects measurements, and what the filter properties are for the data, as well as many other aspects of the sensor. Please read the material of sensor specifications available on the learning platform. Now to an example. The resolution in the unit degrees per second in the specification now shown can be derived from dividing the full range by the number of bits. Here 800 degrees per second by the levels provided by 24-bit resolution. That is, 800 divided by 2 to the power of 24. This is 800 divided by approximately 17 million. Is this a reasonable resolution for an automotive system? Maybe not. This particular sensor has a higher specification than typical automotive sensors, but it is used here as a demonstration. The types of intra-vehicle sensors you have been introduced to in this lecture are used both in passive and active safety applications and in automated vehicles. Following videos will cover other sensors, typically not used for passive safety applications.